Hello students, welcome to EPG Pathshala. I am Dr. P.K. Aluwalia from Physics Department, Himachal Pradesh University, Shimla. Today we are going to discuss about a module entitled Gibbs Paradox and Indistinguishability of Particles from the paper Statistical Mechanics. So students, let us see what we are going to learn in this module. We intend to comprehend the logical consequences of violation of extensiveness of a thermodynamic physical quantity while applying statistical methods. Appreciate paradoxical situation which arises on mixing of same type of ideal gases together, namely Gibbs paradox. Infer the importance of indistinguishability of particles even in a classical system. Correct the expression of entropy of an ideal gas by applying so-called correct Boltzmann counting rule. Learn that quantum statistical mechanics reduces to classical statistical mechanics results only when correct enumeration rules are applied in the classical limit. This module has been developed for postgraduate level as per the following subtopics: violation of extensiveness of entropy S, entropy of mixing of two ideal gases, ad hoc resolution of Gibbs paradox, Sackur-Tetrode equation and thermodynamic properties of a classical ideal gas, indistinguishability and enumeration of states. In this module, we are going to look at a paradox which arose with the development of the statistical mechanics, and this was because of a very simple observation when we derived entropy for an ideal gas, and we found that entropy, which has to be an extensive quantity, was not turning out to be an extensive. So there was a situation which was very paradoxical. An extensive quantity was a non-extensive quantity, and this is what we are going to look at length in this particular module. Before we proceed in this module, let us recapitulate. In this module, we pay attention to the expression obtained for entropy of a monoatomic ideal gas derived in module 8, which is S is equal to n kb log of V upon h cube multiplied by 4 pi m e divided by 3 n raised to power 3 by 2 plus 3 upon 2 n kb, where E is equal to 3 by 2 n kbt. One of the interesting observations is that entropy as given in equation 1 led to correct equation of state for an ideal gas and other thermodynamic properties. Despite these successes, this expression lacks one of the most important properties of entropy called extensiveness, which implies that entropy scales if we scale the extensive parameters involved in the expression. This implies entropy as a function of alpha times n, alpha times v, and alpha times e is equal to alpha times the entropy as a function of n, e, and v. In this module, we seek to look for the implications of the lack of extensiveness of the entropy S leading to Gibbs paradox and how this paradox can be resolved, bringing into focus the issue of indistinguishability of particles involved. Violation of extensiveness of entropy S. To check the extensiveness of entropy S as a function of n, e, and v given in equation 1, let us change n to alpha times n, v to alpha times v, and e to alpha times e, keeping the intensive variables unchanged. Then equation 1 becomes S as a function of alpha times n, alpha times v, and alpha times e is equal to alpha times n multiplied by Boltzmann constant multiplied by log of alpha times V divided by h cube multiplied by 4 pi m alpha times E divided by 3 times alpha times n raised to power 3 by 2 plus 3 by 2 n times alpha multiplied by Boltzmann constant is not equal to alpha times S as a function of n, E and V. Obviously, alpha sitting with V inside the argument of log fails to make entropy extensive. This means that if system is made up of alpha parts, each having entropy S, then the sum of the entropies of each parts is not equal to alpha times S. This is physically unacceptable situation. Entropy of mixing of two ideal gases. To fully see the implication of the violation of extensiveness of entropy, Gibbs went for a thought experiment of mixing of two samples of different ideal gases at the same temperature T, followed by mixing of two samples of same ideal gas at the same temperature. It is worth noting that first part of the experiment involves mixing of different ideal gases and is an irreversible process for which change in entropy is greater than 0. Whereas second experiment involving mixing of two samples of same gas is a reversible process, that is, change in entropy should be equal to 0. Let us see these two cases separately and calculate entropy explicitly using equation 1. Case 1. Mixing of two samples of two different ideal gases at same temperature having same number density. Figure 1 shows the two different ideal gases 1 and 2 at the same temperature and having same number density, that is N1 upon V1 is equal to N2 upon V2. Before mixing, the entropy of two gases are respectively Si is equal to Ni Kb log of Vi upon h cube multiplied by 2 pi mi Kb T raised to power 3 by 2 plus 3 by 2 n Kb, where I is equal to 1 and 2, or Si is equal to Ni Kb log of Vi plus 3 by 2 Ni Kb multiplied by log of 2 pi mi kbt divided by h square plus 1, where I is equal to 1 and 2 again. After the mixing has taken place, the total entropy can be written easily, keeping in mind that now the partition of figure 1 has been removed and each particle of the gas can roam in total volume V is equal to V1 plus V2, so that total entropy can be written as S total is equal to summation over I is equal to 1 to 2 Ni Kb log of V plus 3 by 2 Ni Kb multiplied by log of 2 pi mi kbt divided by Planck's constant square plus 1. Now we can define entropy of mixing as delta S is equal to S total minus summation over I is equal to 1 to 2 Si. Using 4 and 5, this leads to delta S is equal to Kb multiplied by N1 log of V upon V1 plus N2 log of V upon V2, where V is equal to V1 plus V2. Since V is greater than V1 and V is greater than V2, delta S is greater than 0. Hence, process is irreversible, expected for mixing. Furthermore, since we assumed that the number density is same, equation 7 can also be written as delta S is equal to Kb multiplied by N1 log of N1 plus N2 divided by N1 plus N2 log of N1 plus N2 divided by V2. Once again, delta S is greater than 0. Case 2. Mixing of two samples of same ideal gases at same temperature having same number density. Now let us look at the same mixing process by taking in the two compartments same gas and remove the partition allowing for mixing the gases of the two compartments. Only difference now is that M1 is equal to M2 is equal to M, so that S total becomes S total is equal to N Kb log of V plus 3 by 2 nkb multiplied by log of 2 pi mkbt divided by h square plus 1, where n is equal to n1 plus n2. Using this expression and the expression, the entropy of mixing again remains the same as given in equation 8 with delta S greater than 0. This is where the paradox arises. Mixing of two samples of the same gas, again when temperature T and number density are same, can be undone merely by inserting the partition, making the whole process reversible, and the entropy of mixing delta S should be equal to 0, which is not the case. In literature, this is known as Gibbs paradox. Let us now look at how Gibbs paradox was resolved in an ad hoc manner. As discussed in case 2, there is a need to give a careful look to equation 1 so that entropy doesn't remain non-extensive, and paradox of entropy of mixing delta S of two samples of the same gas does not become greater than 0 for a reversible process. Gibbs proposed an ad hoc way of overcoming this paradox by suggesting that from equation 1, if we subtract log of n factorial, the entropy of mixing for case 2 becomes 0 and restores extensiveness of the entropy of a monoatomic ideal gas. This is equivalent to diminishing S1 by log of n1 factorial and S2 by log of n2 factorial and S by log of n factorial. If we do this, equation 1 becomes S is equal to nkb log of V upon h cube multiplied by 4 pi me divided by 3n raised to power 3 by 2 plus 3 by 2 nkb minus kb log of n factorial, or S is equal to nkb log of V upon h cube multiplied by 4 pi me divided by 3n raised to power 3 by 2 plus 3 by 2 nkb minus kb n log of n minus n, or S is equal to nkb log of V upon n multiplied by 4 pi me divided by 3n h raised to power 3 by 2 plus 5 upon 2 n k b. And hence energy E after simplification can be written as E is equal to 3h square n raised to power 5 by 3 divided by 4 pi m V raised to power 2 by 3 exponential 2s upon 3nk minus 5 upon 3. A mere glance at equation 12 tells us that entropy has become extensive with a factor of n dividing V inside the logarithmic term. Let us see introducing this ad hoc term physically amounts to doing what. This amounts to diminishing the number of microstates of the monoatomic ideal gas by a factor of n factorial, involving new counting procedure called correct Boltzmann counting process. If we recall problems which we have done in permutations and combinations which allow us to count without counting, the number of permutations of n different things taken n at a time is given by n factorial. But if all the n things are identical, it should lead to one possibility only. This requires us to divide n factorial by n factorial. So, while checking the extensiveness of the equation 1, therefore, need is to revisit the process of counting of microstates of a monoatomic ideal gas, and division by n factorial, an ad hoc solution to Gibbs paradox, amounts to saying that though we are dealing with the classical particles constituting the ideal gas, still these should be treated as identical to get physically correct entropy. This expression for entropy in equation 12 of an ideal gas was first calculated by O. Secour and H. Tetrode in a series of papers separately during 1911 and 1912, using for the first time quantization of phase space in classical statistical mechanics. Remaining thermodynamic properties of an ideal gas. Now in the following, we derive three very important properties which we left out in module 8. Since without correct and hence E, these physical properties would not have come correct. So let's look at first the chemical potential. Chemical potential is defined as mu is equal to partial derivative of E with respect to N at constant V and S. Therefore, mu is equal to 3h square n raised to power 5 by 3 divided by 4 pi m v raised to power 2 by 3 multiplied by 5 upon 3n minus 2s upon 3n square kb multiplied by e raised to power 2s divided by 3n kb minus 5 upon 3, or mu is equal to 5 upon 3n minus 2s upon 3n square kb into E. In terms of n, v and t, 15 can be written as mu is equal to kbt log of n upon v h square upon 2 pi m kbt raised to power 3 by 2. It is interesting to note that in classical limit, when particle density is low and temperature very high, n upon v is very much less than h square upon 2 pi m kbt raised to power 3 by 2. This implies that the argument of logarithmic term is always less than 1 and hence chemical potential is always negative. The quantity 2 pi m kbt upon h raised to power half is called thermal de Broglie wavelength, which we will see again and again in statistical mechanics. Gibbs free energy. Gibbs free energy is defined as G is equal to mu times n. Therefore, G is equal to n kbt log of n upon v h square upon 2 pi m kbt raised to power 3 by 2. Helmholtz free energy can now be calculated. Helmholtz free energy has been defined as F is equal to E minus Ts is equal to G minus PV is equal to mu n minus n kbt. Therefore, F is equal to n kbt log of n upon v multiplied by h square upon 2 pi m kbt raised to power 3 by 2 minus 1. Indistinguishability and enumeration of microstates. Indistinguishability of particles in a classical ideal gas means that by no means you can tag these particles as particle A and particle B and particle C and so on. At the most we can talk about is the distribution of these indistinguishable particles over different states, say Ni particles over the state epsilon I, giving a set of number of particles Ni distributed over a set of states epsilon I such that summation over I Ni is equal to capital N and summation over I Ni epsilon I is equal to E. We shall carefully look at the emerging situation. The total number of permutations of n particles distributed according to the set Ni is like distributing n particles such that n1 particles are of the kind sitting in state epsilon 1, n2 particles are of the kind sitting in state epsilon 2 and so on. Thus, the total number of permutations turn out to be n factorial divided by n1 factorial into n2 factorial and so on, where the set Ni satisfies the two constraints corresponding to the total number of particles and total energy stated above. If all the particles had been distinguishable, this would have given us the correct number of microstates of a given macrostate. But because particles are indistinguishable, each of these microstates gives one and only one microstate. So Gibbs remedy dividing by n factorial still leaves us with a superior weight factor 1 upon n1 factorial multiplied by n2 factorial and so on. The only way to make it 1 is probability of each of Ni greater than 1 becomes smaller and smaller, and most of the time it takes values either 0 or 1 and rarely greater than 1. This will bring the expectation value of Ni very much less than 1, which defines the classical limit. This leads to correct enumeration of microstates of a given macrostate, which however can be understood only by quantum statistics and not otherwise. So students, let us now summarize what we have learnt in this module. In this module, we have learnt that treating monoatomic ideal gas as made up of distinguishable particles leads to physically incorrect expression for entropy, violating its extensiveness. That mixing two samples of same ideal gas wrongly leads to this process to be irreversible, once again unacceptable physically, called Gibbs paradox. That to resolve Gibbs paradox, number of microstates need to be reduced, implying treating gas as made up of indistinguishable particles. That corrected form of entropy allows calculation of thermodynamic properties such as chemical potential mu, Gibbs free energy G, and Helmholtz free energy F, which would have otherwise been wrong. That enumeration of correct microstates is basically a quantum phenomenon, and in the context of a classical ideal gas requires classical limit to be satisfied. That is, expectation value of occupation number must be very less than 1. Thank you.